So our next speaker, second speaker for this second session in the morning here is Nick Dexter. So he's from Simon Fraser University, and he's going to talk about learning high-dimensional Hilbert-valued functions with deep neural networks from limited data. So thank you very much for giving this this presentation today.
Yes, and thank you to the organizers also for the opportunity to speak. Some of this is joint work with my collaborator Ben Adcock and his students, and also Simone Brugipaia at Concordia University. And then also I'll talk a little bit about previous work with Huang Tran and Clayton Webster. Okay, so the basic problem that I'm going to focus on, the motivation for a lot of this is we have some black box model and we have some input Y. We get an output U, which is in some space V, and we want to use U to compute some quantity of interest, Q of U, which could be a real valued quantity. And we consider, for example, the parameterized PDE, where we have X is the spatial temporal variable, Y is the parameter variable, and L sub X is a differential operator in X. And then V is the solution space of the PDE. So for example, it could be a Hilbert or a Banach space, depending on the PDE. And then of course, the goal is to cheaply approximate a quantity of interest, F equal to Q of U of X or Y, which is a function of X or Y. For example, we could be interested in the parametric function where we compute the spatial mean and look at its dependence with respect to Y. Or we could be also interested in looking at things like the expectation or the variance of the solution. And then we get something that lives in the space V, and we can plot this pointwise, for example, if we're interested in looking at local behavior. Of course, there's many challenges in UQ. The biggest one, of course, is the dimensionality of the problem. Often in these problems, the dimension D is much larger than 1. And then, of course, we run into issues like the cursive dimensionality. Other confounding issues are the complexity of the problem itself. So the solution space, like I said, is often an infinite dimensional Hilbert or Banach space V, which requires further discretization over omega. And so then computing samples of our PDE solution is expensive. And then other constraints, the domain of interest could be irregular or unknown, which could lead to potential wasted samples. And the approximations may require multiple QOIs be computed, quantities of interest, and therefore it's desirable to obtain a cheap surrogate of the solution map Y maps to U of Y. But however, in these settings, we can often exploit structure of the solutions to get an approximation. So we're typically working under the assumption that there exists some typically unknown parameter rho, such that the solution is holomorphic with respect to the parameter variable Y in some Bernstein polyellipse, which is just the tensorization of these one-dimensional ellipses in the complex plane. And then under that assumption, we can show that many different parameterized PDEs that we might be interested in are actually holomorphic with respect to Y. And then, of course, we don't know these values rho, and so we're often in the situation where we're working where the values rho j may differ in scale according to the smoothness in each coordinate direction. And so if we just apply standard isotropic approximations like total degree or tensor products, we can end up wasting effort computing solutions that don't actually decrease the error measurably. And so the last 10 years of research has largely focused on methods to exploit this nonlinear low-dimensional structure, leading to algorithms which achieve exponential convergence. So the standard setup is that we approximate with a multivariate orthonormal polynomial expansion. So here we have U as a unit hypercube and rho as a tensor product probability measure on U. And then the psi sub nu here are the corresponding orthonormal polynomial basis of L2 of U with respect to the measure rho. And these are just the tensorizations of the products of the one-dimensional polynomials in each direction. And of course, depending on the measure, you could end up with the Legendre polynomials or the Chebyshev polynomials. And then the goal is to try to find an approximation to this quantity. U is equal to the sum over nu and N0D, so all multi-indices, C nu, psi nu, where the C nus here are just the inner products of the solution against the basis functions, and they're elements of V, the Hilbert space or Banach space. So the first step typically in these types of things is to truncate U in a basis selected a priori indexed by some set J. So here we're approximating U by first truncating onto some set J, where J has cardinality N. And here are some common isotropic choices of J. We have the tensor product and the total degree, which I mentioned, but we also have the hyperbolic cross and the Smolyak index sets. Each choice here that we could induces a truncation error, eta sub J, which is just the difference between our solution and the approximation on the set J. And then the optimal choice is, of course, the S most effective indices to minimize eta, but in general, we don't know what those indices are. A priori, we actually have to solve for them to find them. And of course, the other thing is that this was kind of alluded to in the curse of dimensionality, but the algorithm costs scale poorly with the dimension. As N here, the cardinality of these index sets grows quickly with D, and that leads to the complexity of the algorithms also growing quickly with D.
So what's the scaling of N with D here with these different choices?
It could be exponential. So for example, in the tensor products case, we have P to the D if you choose a tensor product polynomial space. If you choose something like the total degree space, then you get N plus P choose P, which is also blowing up exponentially with the dimension. But let me just continue on to now some benchmark results. So when we know that U is holomorphic in the Bernstein polyellipse, we can show that best S term Legendre Chebyshev approximations obtain this error that scales algebraically with the sparsity level. So here, to get the best S term approximation, we just choose the largest coefficients of that expansion in magnitude and then just approximate with those coefficients. But these are not constructive approximations. They require oracle knowledge of the coefficients. We have to know all of the coefficients a priori in order to construct this approximation. The constants are also inaccessible, and faster rates often are tied with larger constants in these estimates. And I'll note also that these estimates also hold in the infinite dimensional case for suitable choices of rho and P. We could also talk about quasi-optimal approximations where we take some bounding function B of nu, which we know that bounds the coefficients in norm. For example, like B of nu is equal to C times rho to the minus nu, and then approximate U using the S largest of these bounds, where we order them in this way. And then we can get things like exponential rates of convergence. And I'll remark that just as in the best S term case, this depends on the largest rho such that U is analytic on E sub rho or holomorphic. And constants and dimension dependence are explicit in these results, but we often require sharp bounds on the coefficients in order to show such things. So now let me talk a little bit about compressed sensing. So compressed sensing started around 2005. The goal is to find a sparse solution to an underdetermined linear system, AX equals B, where A is your measurement matrix and B is your data. We note that a vector is sparse if it has at most S non-zero entries. And the key point is that the location of these non-zero entries are unknown a priori. And the reason that this works is we can solve this L1 minimization problem where we know that the L1 norm promotes sparse solutions. And the rationale is that there exist matrices A with M proportional to S log S, rows for which any S sparse vector X is the unique solution of this L1 minimization problem. And there's lots of examples where this is satisfied and lots of applications for compressed sensing, but let me just focus on the function approximation case. So we can incorporate structure to further enhance compressed sensing by considering a weighted version of the L1 minimization problem. Here, this is the quadratically constrained basis pursuit problem. Here, to do approximation in polynomials, we have to set A to be a specific type of matrix based on bounded orthonormal systems. And then we use a weighted L1 norm instead of the standard L1 norm, and W is chosen to promote desired structure in the coefficient vector that we want to recover. One type of structure that we could consider is a lower set structure. And so a lower set is a set where if you have nu in your set and you have mu is less than or equal to nu component-wise, then mu is also an element of that set. So here's some examples of a lower set, and then two examples where we don't have a lower set because this is missing an index here, and then this is also missing an index here. And the rationale for considering lower sets is that smooth functions often have largest coefficients belonging to lower sets. But the question that we had was, what kind of weights enforce the lower set structure in polynomial approximation? Well, in a series of papers, and I think this paper, the last paper here, Adcock, Bourgeois, and Webster, was the first to call or term them the intrinsic weights. We studied these weights here that are chosen as the L infinity norms of the basis functions that we're approximating in. So for the Legendre polynomials, we end up with this product over the dimensions, 2 nu I sub 1, or 2 nu I plus 1 square root. And if you use these types of weights, you can show that, or you can actually observe in practice that approximating some very sparse example functions, for example, this function here is the exponential of minus the sum of cosines over 8d. It decays very quickly in the orthonormal basis, especially when we look at the coefficients sorted by magnitude here in the middle. You can see that you need very few coefficients to get down to order 10 to the minus 16. And then you can see also that using the intrinsic choice of weights, the red weights here, produces the approximation that's best out of all of these examples in both an 8 and a 16-dimensional problem. Okay. So something that I worked on in my PhD thesis was actually taking compressed sensing and applying this compressed sensing framework to the approximation, the fully discrete approximation of solutions to parameterized PDEs. And we came up with this framework called simultaneous compressed sensing, where you replace the norms that I just considered in the weighted L1 minimization problem with a norm that's based off of this V norm. So here, instead of the absolute value of the coefficients, I replace that with the V norm of the coefficients. And I consider my vector as a solution to this problem as a Hilbert-valued or a Banach-valued vector, meaning that the coefficients of this vector, the components of the vector, actually lie in a Hilbert space or a Banach space. And so we applied this in a couple of really neat examples, solving parameterized elliptic PDEs with log transformed affine diffusion in 17 dimensions. And we observed that it obtained better performance than, say, stochastic collocation isotropic approximations in Monte Carlo in this particular example, getting the same amount of, or the same error with far fewer samples. Okay, so something that I was working with Ben on recently was this paper, The Gap Between Theory and Practice. And in this paper, we, a function approximation with deep neural networks. In this paper, we showed this result that says that compressed sensing actually gets exponential convergence on such problems. So if you have a holomorphic function and you choose the hyperbolic cross multi-index set and you solve this weighted square root lasso problem with these intrinsic weights, then you get an exponential rate of convergence that looks like this. And moreover, the sample complexity M scales quadratically in S up to logarithmic factors, which is beneficial because then we don't need to have so many samples of PD solution. Okay, so the other takeaway, though, is that these results directly apply also to the simultaneous compressed sensing method with finite element, and we can actually show that we achieve the state of the art in these types of problems, in that we have the same stability properties that are inherited from compressed sensing, the same accuracy that we get from this result, and also the same sample complexity. So that, you know, in theory and in practice, we expect that very few samples of the solution are needed to actually reconstruct these types of PD solutions. Okay, so now on to neural networks. Over the past decade, we've of course seen neural networks have increasing use in a wide variety of these very historically challenging application areas. And the broad questions that we had when I started working with Ben was, should these techniques be used in computational science and engineering, for example, high dimensional parametric PD problems? Can we leverage this low dimensional structure that I was talking about with polynomial approximation efficiently with deep neural networks? And are current methods of training actually capable of producing DNNs competitive with state-of-the-art approaches? So we had this theorem, this practical existence theorem in the Gap Between Theory and Practice paper. The reference is right down here, by the way. It says that there exists a training procedure based on minimizing a regularized L2 loss function for which there are minimizers that perform as well up to a constant as compressed sensing on these types of problems in terms of accuracy and sample complexity. So the big question was, is it possible to actually achieve these results in practice with current methods? And so part of my work was also to develop this framework called MLFA, which is the machine learning function approximation framework. This utilizes rigorous testing principles in terms of testing and training splits of the data, repeatable experiments, and averaging the results over multiple trials. And it also allows for computation of errors and global norms that are comparable with other methods. So let me give you a little bit of the setup, and then I'll show you some numerical examples. So Here, the problem is we're given some random measurements of a function. We want to approximate the function. So the architectures that we considered in that paper were the fully connected ReLU deep neural networks of different depth and width. We implemented everything in TensorFlow and MATLAB for the data and compressed sensing approximations. And then we used random initializations, Atom Optimizer, 50,000 epochs of training, and a loss tolerance of 10 to the minus 7, and then run 20 random trials, each with different seeds, and computed these on the Cedar compute cluster at SFU. And the testing data that we used, in contrast to the random measurements, we used deterministic sparse grid quadrature testing data. Okay, so here's a very simple example approximating this function f here with ReLU networks that have 4 hidden layers and 40 nodes on each hidden layer. And you can see the approximation is not so good, but if I continue to increase the depth and the width at the same time, then you can see that as I increase the width and the depth, the approximations actually get noticeably better in just the eyeball norm here. So going to 20 hidden layers and 200 nodes per layer, you can see that compared to with just 4 layers and 40 hidden nodes per layer, we get a much better approximation on average with these trained neural networks. However, if you keep going, say to 20 hidden layers and 800 now hidden nodes per hidden layer, then you can start to see we get these really unstable networks where we have these spikes and weird artifacts from the training. Now on the same function,
just kind of curious, these instabilities, are they sensitive to the way you initialize the neural networks, or did you try that?
Yeah, we tried many different types of initialization, but ultimately we found pretty much the same results in all cases. So this slide here shows that if I actually look at this function and compute its orthogonal, its expansion in the Legendre basis and look at the coefficients of that expansion, the function is actually very, what we would call compressible in the sense that the coefficients decay very quickly to 0 with increasing order. But then when I compare the results of solving or approximating this function with deep neural networks and compressed sensing, the compressed sensing here is the dark red line with no dashes and the blue line here for weighted L1 minimization. And here you can see a variety of different neural networks start to do better as I increase the depth of the network and the width of the network at the same time. And ultimately the 10 hidden layer with 100 nodes per layer and 20 hidden layer with 200 nodes per layer networks do the best. Also, I plot over here the weights of the networks because we were interested at the time to see whether or not the weights are growing as you increase the size of the network. But actually the opposite happens. The weights are actually much smaller as you increase the size of the network. And here's the same function, but I've modified the coefficients inside the sine functions to be 10 times larger. And now you can see that the coefficients decay much more slowly in the Legendre basis. And also now you can see pretty much the same, a little bit about the same performance here for the neural networks compared to compressed sensing on this one-dimensional function. But instead of being very, very small now, the weights are a lot larger, maybe 5 or 10 times larger than they were previously. And this function is a lot less regular. Okay, so now let's look at a higher dimensional, eight-dimensional example here where I've got this function e to the minus sum of the cosines from previous. And again, this function is very sparse. And then when I look at the approximations obtained with the ReLU deep neural networks compared to the compressed sensing approximation, it's not even close. Like we're off by several orders of magnitude here. And again, the neural networks are not learning huge weights here. They're learning something very close to the initialization that we chose. And then this is a little bit less regular function where the decay of the coefficients is a lot slower. And again, we see the same kind of thing with the weights not being too large, but maybe a little bit larger than the previous example. But now when we compare the performance of compressed sensing with the basis of say 5,000 or approximately 5,000 elements, we see that the neural networks are actually doing performing competitively with the compressed sensing approach. So the key takeaways is that there's a large gap between theory and the practice in these results. Surprisingly, the performance is comparatively worse on functions which are most well approximated by polynomials. And sometimes these deeper networks can do better, but but this isn't always the case. And if you take architectures that are too large, you can lead to unstable trained networks. And the accuracies, of course, are limited by the precision used. We looked at double and single precision training for the neural networks, but we never saw anything get close to order machine epsilon in terms of the testing error. Well, we did see that with the loss functions in the training error. Okay, so very quickly, we can modify the standard architecture for function approximation to approximate parameterized PDE problems. So here we consider the same kind of architecture, except instead of a scalar valued output, we have RK valued output. And that's because we want to approximate directly the coefficients of the finite element expansion of the function in the finite element basis. So my phi k here, these are the finite element basis functions, and I'm using the neural network to compute the coefficients of the expansion with respect to that basis. And then I also use standard finite elements to solve for these coefficients otherwise. And the reason we want to do this, of course, is because there exists this DNN existence theory that says we can get the same kind of exponential rates of convergence with deep neural networks. Here we're approximating directly this solution map y maps to u of y, but we're doing so in the finite dimensional finite element space v sub h. So we're given these measurements to the form di is equal to u plus yi, where we have some extra error term here. And these measurement errors could come from the numerical PDE solver or some other source. And the goal is, again, to approximate the DNN, the function with the DNN. We can do this by training with the mean squared error. We can also consider this mean v-norm squared error that was proposed by Geist, Peterson, Raslin, Snyder, and Kuteniuk. The same exact setup as we used for function approximation, just with the different architectures here to approximate the finite element solutions, same exact testing setup. Here's what the training error looks like.
So just another, sorry, just another quick question. So, oh yeah, you did try different activation functions. Oh, sorry, I was just about to ask about that.
Yeah, sorry, I had to go back real quick to, here's the activations functions that we considered were hyperbolic tangent, ReLU, and leaky ReLU deep neural networks.
Okay, sorry, yeah, okay, thanks.
So that means that every activation function in the neural network is either a ReLU, a leaky ReLU, or a tangent, hyperbolic tangent. The left column here compares the mean square error. The right column here compares the mean v-norm squared error. I'll note that the mean v-norm squared errors, the losses are these lines up at the top here, but the mean square error, the loss is down here at the bottom. Those are the ones with the circles instead of pluses, although that might be kind of hard to see in this graph. And then when we look at the testing error, so this is with respect to epochs of training. So this is, I think, 50,000 epochs of training. We looked at the testing error in these global norms, and we see that the networks trained with the mean square error do the best, and in particular, networks with about 50 nodes per hidden layer and about 5 hidden layers do the best out of all the ones we considered. Same thing with the different error metric here with the H1 norm instead of the L2 norm. These are the training times for these networks. So you can see a scaling that looks like this as you increase the number of epochs of training and the amount of data, or I'm sorry, and not the amount of data, the mean square error versus the VNSE.
So I'm sorry, it's going a little fast here. So the MV, what's MV NSE here?
Mean v-norm squared error. So that was the error right here.
Okay, so it's all the sum. Okay, all right.
Yeah,
okay,
here we're looking at just the error in the global v-norm over the parameter.
But you're not comparing against the polynomial basis.
Right, yeah, we're just using the global error right here to train. This is just the training error, the training loss function. Okay. So here's a prediction of the solution early in the training after 2 epochs of Adam. Here's what it looks like after 2045 epochs, and this is the mean square error we got at the end. And then here is a 30-dimensional example with parametric diffusion, log transformed affine diffusion coefficient based on this example from Nobilian et al. And here you can see many different architectures are plotted. But the important point is that this dark or this filled blue line here is the compressed sensing based or simultaneous compressed sensing based approach. And the lines with the triangles here are the hyperbolic tangent networks, and they perform the best overall. So the conclusion is by tuning not necessarily theory-based architectures and training, we're able to match or outperform these state-of-the-art methods with deep neural networks. I think my time is pretty short, so maybe I'll just stop here with these remarks and open up to questions if there's any time.
Okay, so any questions from the audience here? So I just had a quick question about the optimizer that you used. Did you try like BFGS or LBFGS
we didn't
optimizers?
try those two. We tried Atom, SGD, Atom W, which is this weight decay version of Atom, and I think a couple others, but I can't remember them all off the top of my head. This was mostly in the MLFA study, the gap between theory and practice on with function approximation on deep neural networks. And the reference for that paper is right here, by the way. So I think in the appendices of that paper, we showed a comparison with multiple training algorithms.
All right. So, okay. Well, thank you very much for your talk. Awesome. Yeah. Thanks. Great. Very, very interesting discussion of